Well, more importantly, it's the square difference between the observed frequencies and the expected frequencies relative to the expected frequencies. So the chi-square test statistic is the observed frequencies minus the expected frequencies squared, okay, relative to the expected frequencies. And we do that for all of our categories, okay? And it's the sum of that, okay? It's the magnitude of all of those particular differences. The bigger this chi-squared statistic is, the more evidence to suggest that the difference between the observed and the expected is larger. In other words, that what we've observed actually deviates from what we'd actually expect to happen. Yeah. So actually, what I want to do is I want to calculate all of these z-scores. Okay. Now don't forget the z-scores are based. I'm basing them off the upper bound intervals. So actually, this one will be based off 30. This will be based off 40. This will be based off 50. This will be based off 60, 70, and this is anything that's greater than 70. Okay, which is anything that's less than infinity, I suppose. Okay. And what we're going to do is once we have the z-scores, we're going to calculate the cumulative probabilities, or the area under the curve, under the z curve, yeah, up to well, just less than the actual upper bounds themselves. Okay. So what I'll do is I'll just do one or two z-scores. Okay. So the first z-score that I'd like to do is for this particular 20 here. Okay. So x. I suppose to calculate the z-scores, okay, we need to have an estimate. I suppose I really should be saying here, this is a standardization here with respect to the sample data, it's the sample statistics. Okay, you've probably more than likely seen your z-score to be x minus mu all over sigma. Okay, but to calculate this, we need to know what the population mean is and what the population standard deviation is. Okay, we're going to estimate these two things using x bar and s. Okay, we're just going to use them as estimates. Okay, and then we know from a sampling distribution perspective that we should really have the estimate of the sampling distribution is s over the square root of n, but we're not interested in that here. We just want to just standardize these variables. Okay, so the first case is, well, I need to know what my x bar is and what my s is. In other words, there's a frequency distribution. Here's a grouped frequency distribution. Okay, so I need to calculate what my mean of that is and what my standard deviation is. Now I've already calculated them values. I've already calculated that our x bar for this particular distribution is approximately 46.16, and I've also calculated for this group frequency distribution what the standard deviation is. So for this group frequency distribution, I've calculated my s to be equal to it's approximately equal to 14.91. Okay, so given them values and given these x values here, these upper bounds, these x's, okay, what is the associated z-score? So let's do the first one. So my first z is going to be equal to, well, my first x is 20. So it's going to be 20 minus the mean, which is 46.16, divided by the standard deviation, which is 14.91. Now when I do that on the calculator, okay, that's going to give us a negative test statistic. 20 minus 26.16 is going to be minus 46.16 is going to be minus 26.16. And that needs to be divided by 14.91, which gives us a z-score of our z in this case is going to be equal to minus 1.75 to 2 decimal places. So the z-score here is minus 1.775. Okay, that's our z-score. The second z-score here, actually let's just choose a different z-score. Let's say for 60, the z-score is going to be 60 minus 46.16 divided by 14.91. So that's going to give us a z-score. Okay, so this is the first z-score that I've calculated. Okay, here's the second z-score that I'm calculating. Okay, that's going to give us a z-score of, well, 60 minus 46.16 gives us a value of 13.84. You probably can't see that there. Okay, gives us a value of 13.84, and then I need to divide that by 14.91, which gives us a z-score of approximately 0.93. So that's a z-score of 0.93. So actually I did that for 60, so this z-score is approximately 0.93. Now I've already worked out the z-scores for the others because we don't want to be spending time calculating z-scores. We have got previous videos on how to do them, but I've done them particular calculations already, and what we have is that the z-score is associated with a distribution, okay, with 30 less than and a mean of 46.16 and standard deviation of 14.91. The z-score for this particular value on that distribution, okay, would be minus 1.08. Okay, the next z-score would be minus 0.41. Okay, the next z-score would be 0.23. Okay, 0. Actually, I have 0.2575. Let's say 0.23 here. Okay, 0.23. I'm gonna have a little bit of rounding error here, guys. We've already done the one for 60. Okay, what about for 70? Okay, well the z-score for 70 is going to be where am I going to here? So that's 0. The z-score for, let me just do this here. Am I missing something? Okay, the z-score for 70 is 0.94. The z-score for 60, okay, the z-score for 60 is, well, the upper bound is 60, so its z-score is 0.93. That's perfect. The next one is 1. Sorry, I'm looking at the wrong one. 1.59, which is approximately 1.60. So this is about 1.60. And then the z-score associated with this particular upper bound here, which actually I'm not going to be using, yeah, okay, right? Because actually it's any value greater than or equal to 70, so it's up to infinity, yeah, okay. But we know that the area below that value is going to be 1. It's all the area under the curve, okay. So now that we've calculated the z-scores, what we need to calculate is, for each z-score, can we figure out what the area is below them, okay? So what's the area under a standard normal curve that's centered on 0 with standard deviation of 1? That's our standard normal curve. What's the area to the left hand side of minus 1.75? Okay, so in this case here, I have a standard normal curve. Okay, it's centered on 0, and I want to know, based off minus 1.75, what is the area to the left hand side of it? Okay, now we have a set of tables that allow us to look this up, but I suppose that's equivalent to asking what's the area to the right hand side of 1.75, yeah, okay. So if I was to do that, but anyway, when we look up these particular areas, okay, we're going to look at the area to the left hand. I'm not spending time here calculating areas